So once again, let me introduce myself. I'm Srireka Thoniparambil, EPS-SG User Preparation Project Manager. I'm co-organizing this event with Stefan Budzinski, who is the MTG User Preparation Project Manager. We have Rosa Uluchi, who is offering us the technical support. I welcome all of you to this user preparation webinar on next generation hyperspectral infrared sounders on board the next generation EUMETSAT satellites. We have the infrared sounder IRS on board the Meteosat third generation sounding satellite, so MTGS, which will be launched in 2023. And we have the infrared atmospheric sounding interferometer, next generation, that is IASI-NG, on the METOP second generation A satellite, which will be launched in 2023 as well. So as part of supporting our users in their preparation towards MTG and EPS-SG, and also taking into account the current traveling situation due to COVID-19, we are planning to organize a series of webinars on the observation missions on both MTG and EPS-SG, of which this is the first one in this series. So what we intend to do with these user preparation webinars is to raise awareness among our users and developers. The talks that will be presented today and also yesterday will provide them a good level of scientific and technical understanding. That's our hope. We also plan to trigger, another intention is to trigger developments of software tools which would support the processing, visualization, and analysis of the data products that are coming out of these great missions. We also want to stimulate application developments. So as you know, today is day 2 of the event. We had a very fruitful session yesterday where we had talks that were focusing on the instruments, both IRS and IASI-NG, the measurement techniques, the scan patterns, calibration process, products, their formats and disseminations as well. We also had a dedicated talk on the principal component representation of products. I hope you had a useful session yesterday. You know that while IASI-NG is offering continuity from METOP IASI, we also see that there are a lot of enhancements providing benefits to NWP, atmospheric composition, and other applications. And MTG IRS, on the other hand, is an innovative mission, additionally supporting the nowcasting applications as well. We also saw from yesterday's talk the experts highlighting how both these missions complement each other. Today is a logical continuation of yesterday. We are pleased to see the level of participation yesterday. We had an active question and answer session. Thank you for that. We also had a very good feedback session from you, feedback that you have provided. We also see that today also we have about 100 participants already from different parts of the world. So that's a good sign. We are very happy. So today we had a continuation from yesterday's presentation. So we are focusing today more on geophysical products with more application examples in meteorology and atmospheric chemistry. That's my introduction, but before we start with the presenters, let me remind you that we use Slido for our interaction. This means you can post your questions, comments into Slido. It's very easy to use. You can access Slido on your computer or your phone. You just type in slido.com, then you will be prompted for an event code where you type in NG-HSIR. We will answer all your questions either live or later offline. So please do not hesitate. Just remember that you can also ask anonymously or you can optionally give your names. Actually, Rosa will put all these instructions in the chat, so you don't have to note it while I speak. All the information will be available in the chat. That reminds me that please restrict the use of Zoom chat only for technical problems, like if you can't hear properly or if you can't see the slides, etc. We will try our best to solve problems from our side. Yeah, so please make the session active by posting your questions. We will wait a bit after the talk is over so that you get enough time to type in your questions. Rosa will also activate a poll towards the end of the session. You'll be having some usual survey type questions plus some poll questions, which will help us to improve. Like I mentioned earlier, we will have some more webinars coming on all observation missions, and this will help us to improve how we do this in the future. And again, keep yourself muted. Rosa would anyway mute you all. And also try to switch off your video during the event. This will help us to save some bandwidth. And we will also make the recording, like you have seen. For both days, we are recording the event. The presentations as well as the recordings plus the Q&A will be available after the event. So that's all I wanted to say. With this, I would like to hand over to our first speaker, Thomas August from EUMETSAT. Thomas.
Hi, Sririka, can you hear me?
Yes, yes, Thomas, you can start.
Okay. So I suppose I'll share the screen. Number one. Can you see a blue screen?
We see that, Thomas.
Okay. So you have the audience view now of the presentation.
Yes.
Okay. Good. Good afternoon, everyone. It's my pleasure being with you today. I wished we were able to meet in person, and I hope this time will come soon again. So we're going to talk today about meteorological products from the two future missions, IASI-NG and MTG IRS, whose characteristics were introduced by Dorothee yesterday. As we go and talk about the geophysical products and the applications they support, we'll come back briefly on some of the notions presented yesterday. Naturally, I will use IASI a lot as a reference and heritage to introduce the future missions, in what it is already a very good proxy with real observations to prepare with, and what additional and specific benefits can be expected of the future missions with reference to their improved performances, instrumentally speaking, and the specific acquisition principles. So the hyperspectral measurements, which are represented here for IASI, IASI-NG, and IRS, contain a wealth of geophysical information, which are of great use for a large palette of applications. And we will focus essentially today on the meteorological products in this presentation, so the thermodynamic and cloud products. Okay, that's not working. Let's try again. Okay, click. Okay, and the cloud products. And we will touch on others also important products like the sea surface temperature, the land surface temperature, the land surface emissivity, the dust index, and ozone, which all can be retrieved from these measurements. And all the other atmospheric composition, air quality products will be covered by Pierre Coher after this presentation. So yesterday, Bertrand Theodore walked us through the product's content. And what you are seeing here is the end user performance requirements expressed for IASI-NG. That's expressed in terms of precision in the horizontal and vertical resolution, but also precision of the retrievals. In comparison, I'm going to show the IASI requirements that come now in red. And you can see, let's take, for instance, the example of temperature profiles that where we had the requirements of 1 Kelvin precision on 1 kilometer vertical resolution for IASI. We have now requirements of 0.8 Kelvin and 0.8 kilometer in the lower troposphere and mid troposphere for IASI-NG. And this is the same for all products. So in general, we have higher expectations from the future missions and especially IASI-NG to fulfill the ever more demanding user needs. I will not elaborate much on the atmospheric composition air quality products, which are also required from IASI-NG. I'm giving this table for your reference later. Those will be presented by Pierre after my talk. At this stage, I'd like to mention that MTG IRS did not express their requirements for level 2 products in the same way as IASI or IASI-NG did. They only refer at this stage to the geophysical parameters that are needed and emphasizing the timeliness, as we saw yesterday with Bertrand, and that in general, MTG level 2 products should be as good or improve on the Meteosat second generation. This is why they are not presented here, but importantly also, MTG IRS level 2 include ozone products, and the other atmospheric composition are not in the baseline yet for launch, but will be considered in further evolution. What was not presented yesterday by Bertrand about the IRS Level 2 product is a list of atmospheric stability parameters. They have indeed been added 2 years ago following a request in the IRS Mission Advisory Group. And at the moment, they consist of the following parameters listing here in the table. And in fact, there exists a whole zoo of parameters, and the rationale for this choice was to ensure continuity with MSG Severi global instability indices and consistency with the follow-up MTG FCI. The CAPE and convective inhibition parameters were added because we realized that the forecasters widely rely on these indicators when evaluating atmospheric situations, and also the hyperspectral sonders has a profiling capability. So this list may evolve as we gain experience with users, and we will come back on these studies later. So what I want to give an overview of now is the overall level 2 processing baseline, and you have several blocks. In green will be the common blocks to all missions, and in cyan what is specific to IASI, IASI-NG, and in pink what is specific to MTG IRS. So the first step is to prepare and collocate level 1 information, so the radiances that are transformed in the level 2 processing in principal component, collocate with atlases, and in the case of the polar satellites with microwave information. The first stage is the machine learning based retrieval, which is called PVLR for piecewise linear regression, and that provides all sky retrievals of temperature, humidity, surface temperature, ozone, land emissivity, cloud signals, and that is making use, in the case of IASI and IASI-NG, of the microwaves. In addition, then comes a cloud retrieval where we derive a cloud mask, retrieve a cloud fraction, cloud top height, and a dust index. And for the clear cases only do we fine-tune the retrievals of temperature, humidity, and ozone and surface temperature with an optimal estimation. And that is solely based on the infrared measurements. So in green, this is the common blocks for all 3 missions. And these 2 stages are so-called physical, but based on variational methods. Then eventually in the EPS-SG and EPS worlds, we have a last block of atmospheric composition retrievals, most of it consisting of ACSAF provided libraries. And specific to MTG IRS, we have a parallax correction and the series of stability indices which are introduced before. So in the following, we will walk together through all the meteorological products currently in operations and planned in the future missions. And we will get a glimpse at illustrative validation results just to illustrate their performances. So we start with the sea surface temperature, illustrated here with IASI level 2. And the sea surface temperature of IASI, but later with IASI-NG as well as with MTG IRS, will contribute to the group of high resolution SST through partnerships with the OSISAF. The quality control to retain the SST retrieval for this project is based on intrinsic uncertainty estimate that we provide along with the retrievals, as well as cloud and dust retrieval signals. What you're seeing here on the left-hand side is the typical yield of good SST products that we retain for day and night time. And at the right panel, we have comparison to Ostia from the routine monitoring of METIS, showing the very good precision and that we have hardly any bias. So we are within the requirements with IASI, and we even ambition to do better with IASI-NG. So I'll move now to the land surface temperature, and I'm showing here results of a validation performed quite some years ago in a dedicated effort during METOP B commissioning, but the conclusions still apply, where we could verify that the retrievals from IASI, illustrated with the dots here, match well the in situ measurements from this validation site in Gobabeb in Namibia, and in what they can be complementary to the forecast, which tend to be accurate at night, but not necessarily be able to capture the full diurnal cycle, especially in these places during daytime. Then we move on to the, why isn't it working? I apologize, my computer has frozen now. Okay. Okay, so we continue with the lens surface emissivity, which is a difficult product to validate because there aren't really direct objective reference measurements for it. And one way of assessing the quality of the lens surface emissivity, which I'm showing 3 examples of the daily maps that we can get from method A, B, and C, is actually to see how well the retrieved emissivity could help fitting the observations through radiative transfer calculations. And this is the object of the plot here on the left-hand side, where you see the standard deviation ops minus calc computed with the retrieved surface emissivity in the red curve, and with a static atlas, which is a very good one, by the way. The camel static atlas is the black curve. So you see that with using retrievals, we can fit better the observations, which indirectly speaks about the quality of these data. Okay, the cloud mask here, jumping to another topic. We structure the cloud mask in 4 stages. First, the pixels for which we are really confident that the scene is cloud-free, pixels where we believe this is likely clear, but potential small cloud contamination is possible. And the third stage is where the scene is likely clear, or you could translate also partly clear. And the last stage is the cloud signal is so strong that we are really sure this is a cloud. So to illustrate the cloud products, the mask from the detection, but also the effective cloud amount, the cloud top height, I will now jump to another tool. Let's see if it works interactively. Okay, I hope you all can see the Google Earth view. You have the AVHR imagery and overlaid on it the cloudiness mask I just presented. So we're going to zoom in now and move to the, for instance, let's take the Mediterranean area. And you see, again, the color scale which I presented yesterday. Dark blue, we are pretty sure this is clear. Cyan, this is likely clear. Yellow is likely cloudy, and that corresponds to actually partly cloudy pixels. And brown, red is the cloudy pixels for sure. So you can have an impression of the quality of the mask. I'm going to jump now over to the cloud top pressure, or the cloud fraction. Let's take the cloud fraction, sorry. Okay, which is another parameter that we provide. And you see here the color scale from 0 to 200, and you can tell that within the thick clouds we are at 100%, and at the edges of the cloud we are around 10, 15% or below. So the cloud fraction is working well. And so is also the cloud top pressure, but in the interest of time, I will skip over and come back to the presentation now. So the next parameter along with the scene characterization is the dust index. And the dust index we provide is a pseudo-quantitative indication of the dust signal. An example of a daily map is shown here in the upper right corner from IASI. It was trained by simple regression using real observations and manual classification, a method developed by Liv and Clarice from University Libre de Bruxelles. It has no units, but is a good indicator of the aerosol dust load, as could be verified by comparison against an independent satellite product, namely the ATSR ORAC from Oxford RAL. And the good correlation is shown here on the left-hand side, where you see the aerosol index derived from IASI compared to the AOD of ATSR in different dust modes. And here you see an overlay qualitatively. Oops. Anyway, it's frozen again, so I might skip over that one. Don't know what's going on here. Okay, well, so much for the dust. Okay, we'll come back to that later if you're interested. Anyway, what I want to focus now is on the thermodynamic parameters and come back to the notion of measurements and the spectral resolution that Dorothée introduced yesterday, and now how this translates into atmospheric sounding capabilities. So as we saw yesterday, IASI and its successors in space will have different spectral resolution, IASI-NG being the most highly resolved, IASI in the middle, and MTG IRS slightly less than the others. So we will try in the next slides to evaluate what it means for temperature, humidity, and ozone sounding. And Pierre Coer will certainly elaborate further on the improved detectability and characterization of the other atmospheric composition and air quality traces. So to get started with, I'm showing here what we call averaging kernels, which is the sensitivity of a retrieved quantity at a given level to the true profile. So in other words, it tells you where the information of a retrieval at a given level, so here, for instance, the humidity at 700 hectopascal, where this information is coming from. So as you, usually it's not a Dirac, it's more of a Gaussian-like mode. And the narrower and pickier the main mode is, the better sensitive and resolved is your retrieval. And the figure in this and the following slides were computed with just one single case with a US standard atmosphere and some assumptions, which, if you're interested, we can discuss later. The purpose here is more illustrative of the order of the expected relative performances between IASI, IASI-NG, and MTG IRS sounding capabilities. So we observe here for humidity, temperature, that as expected, IASI-NG is more highly resolved than IASI and then IRS. And interestingly also that IASI and IRS have similar sensitivity to ozone, and IASI-NG makes a significant difference here. So in terms of relative sounding performances and relative retrieval precision now, these figures show you the expected precision of IASI-NG compared to IRS. And so when the figure goes to the left, this is for an improvement, and when it goes to the right, this is for slightly less good retrievals. So with IASI-NG, we intend to improve the quality of the temperature retrieval by a couple of Kelvin in most of the atmosphere. With IRS in the troposphere, we will not lose much, maybe in the lower strato and upper strato, yes, but that's less relevant for nowcasting, so no big drama. In humidity, we expect an improvement of about 20% in the precision with the IASI-NG, and maybe a degradation of 10 to 20% with the IRS, but in the middle and lower troposphere, this will be relatively limited. Another way of looking at that is looking at what we call the degrees of freedoms, and the graphs here show the cumulative degrees of freedom for signal in temperature, in humidity, and ozone. They are indicative of the actual independent pieces of information in a retrieved profile. And these profiles are sampled on about 100 levels, which we know is far beyond the actual vertical resolution power of such instruments. And so as we go up from the surface up to the top of the atmosphere, we stop accumulating information, which is the case above, say, 200 hectopascal for humidity. And we see that here again, IASI-NG will bring more highly resolved information in the vertical for temperature than IASI and then IRS, same for water vapor and same for ozone. Okay, so these were theoretical estimates. What we wanted here to verify with real observations is what can be expected of IRS in terms of retrieval precision, in complement to the theoretical estimates seen before. So we emulated the IRS level 1 radiances out of real IASI observations in the spectral, but still at the IASI pixel sampling. And we trained the same retrieval method as for IASI, and then we compared to objective independent in situ sound measurements. And this is what these graphs are showing. In red, you have the statistics of IASI retrievals against sounds, so bias and standard deviation for temperature, and then for humidity below. And what I call IRS is actually the pseudo IRS trained in this way. And we see that in line with the theoretical performance assessment, we lose 0.1 to 0.2 Kelvin and 10% precision for temperature and humidity respectively. So in summary, if IASI was said to be 1 Kelvin, 1 kilometer, then IRS is probably going to be like 1.1, 1.2 Kelvin on 1.1, 1.2 kilometer. Okay. So let's continue. It sounds like IRS is slightly less performant than IASI, but in fact, its force and the major advantage is actually very much also in its spatial temporal sampling, in addition to being able to resolve the atmosphere in quite a good way as well. So we illustrate here the respective horizontal sampling and coverage of IASI and IASI-NG, which is represented by the ellipses here, on top of an IRS image. That's a brightness temperature image in the window channel. So that gives you a feeling for the coverage of the two types of missions. And so with a revisit, as we saw yesterday with Dorothée, with a revisit of every half an hour with IRS and a spatial sampling of 7 to 8 kilometers over Europe, as compared to twice a day and 12 to 40 kilometers pixels with polar sonders, IRS is clearly a unique asset, or will be a unique asset once in space, to monitor the atmospheric dynamics. And so the series of measurements that IRS will provide will convey unprecedented 4D information of temperature, humidity, and to some extent ozone, in addition to profiles themselves. We expect them to be able to derive wind information in the vertical too, which is going to be a key input to NWP, for instance. So to sum up, with IRS, we really want to be able to derive and detect and monitor instability before the cloud form and develop, which is so far the way to go with geoimagers. So in short, to be able to gain precision and lead time in the assessment of potential severe weather. So I have talked about the quality of the profiles, but I mentioned also that we provide, along with the profiles, quality indicator. And so these quality indicators are in fact uncertainty estimates. At this stage, for temperature and humidity, they relate to the expected precision in the lower troposphere. The plan in IASI-NG and IRS baseline is to extend the concept and actually provide uncertainty profile estimates. This can be used by the users to perform quality control and acceptance, depending on their own specific requirements and their own applications. So I'm illustrating in this slide and the next one to come, the significance or representativeness of this quality indicator. In this slide, we see the ellipses are IASI pixels, and the color coding is the uncertainty estimate for temperature. And that's overlaid on AVHR true color image. So we have the best retrievals, not surprisingly, around the cloud in the clear cloud-free pixels, and slightly less good retrievals in the cloud. So that was expecting, but I should recall that the quality indicator, or these uncertainty estimates, had no explicit or prior knowledge of the cloud or any other contextual information. It all comes from the radiances and the profiles retrievals themselves. So that's very interesting to confirm that indeed we have best retrievals in cloud-free situations. Another way of looking at the significance of these quality indicators is to stratify comparison of retrievals, temperature, for instance here, to zones in different quality range. And this slide is going to be very busy, but it illustrates very important points, 3 points, and we'll come back to that. So you're seeing here on the left-hand side, the infrared only retrievals compared to zones, bias and standard deviation, and on the right-hand side, the same for combined microwave and infrared. So that one is representative of IASI and IASI-NG to come, and this one more of MTG IRS, which has no microwave companion. These statistics were performed for the quality class with precision below 0.75 Kelvin, and we see indeed that the standard deviation of the comparison to zones is well below 1 Kelvin. When we move to the other class of below 1 Kelvin, we see that the standard deviation is also in most of the troposphere of 1 Kelvin. And as we go on with a subsequent class, 1 to 1.5 Kelvin precision, we see also that it's consistent with the comparison to clouds. And that's true for infrared only and microwave infrared. Only important to note that we have a higher yield of good retrievals with the combined microwave infrared than with infrared only, which is not surprising because in clouds, microwave helps making still good retrievals where infrared only can struggle a little bit. And finally, the last classes, and especially the worst class, is more populated in infrared only than in the combined microwave infrared. So what this shows, the 3 points, it illustrates a good performance of the vertical soundings already, the significance of the uncertainty estimates and in what they relate to the product quality, so they are reliable information. And we show the expected yield and quality of good of products in the combined microwave infrared mode, polar sounding, and the infrared only MTG IRS. I'm approaching the end of the talk, but important to keep in mind is however good the quality is, as we have seen, the vertical resolution is limited by nature of the measurements. The retrieved profiles are a smooth version of the truth, and they usually have a lower sensitivity next to the surface. That is intrinsic to the measurements. It's not a retrieval deficiency. But they are still capable of holding interesting thermodynamic information. And this is what this stephigram illustrates here. It shows conditional instability as observed in the morning by IASI, that's real observations, over the region of Tuzla in Bosnia and Herzegovina. And a couple of hours later, as we will see on this severe image here, there was actually strong big convective cells and storms that is pointed out by the arrow. So there was an interesting instability indication here that relate to actually severe weather later. So because of the quality of these products, and since especially the release of the version 6, that triggered interest in the forecasting community. And although nowcasting was not foreseen as an application in the beginning for IASI and then for IASI-NG, EUMETSAT has established, based on this request, a regional service to fulfill the need of the forecasters to reduce the latency. And with this IASI Level 2 service, we provide retrievals in less than 30 minutes from sensing. And I'm showing two animations in the upper right here to show 3D humidity structures as they are retrieved and disseminated with the IASI Level 2 service. And from this point, a number of application studies involving MET services have been initiated, and they have been very helpful to explore the potential use case of IASI already, but also, and importantly, to grow experience with these products, also raise awareness with the forecasters in preparation of MTG IRS. Now, at this stage, just Sarika, can I take a couple of minutes more to speak very briefly about these application studies?
So actually, yeah, this is still you're running into a Q&A session, but like I said to you before, we have some slack actually for the last session. So how many minutes do you think for the application studies? How many
I think I need
10 slides?
No, it's I need 5 minutes, I think 5-6 minutes.
Definitely, please go on.
Okay, thanks. Yeah, okay. So that is an example of studies we have conducted with the European Severe Storm Lab. And I'll try to show that more dynamically. Okay, I hope you're seeing the screen. So you're seeing here a situation and instability represented with the CAPE index from the model, and I'm going to overlay on it the IASI sounding. And as we move across, then you see two profiles. The thick line is the models, and the thin line is the retrievals of humidity, and same with temperature, and the orange is the CAPE. So this is a tool we're using, and that illustrates also here that we indeed have 3D information. But at this point, really, we should extrapolate what we will be able to see from IRS. That was a qualitative notion I wanted to convey here. Another study is the example of this Shapiro-Kaiser cyclone that was studied by the German weather services. A hurricane that raged in 2013 with a record-breaking wind gust of 190 kilometers an hour. And what is interesting and represented here is that the descending dry stratospheric air, which is typical of the Stingjet area, is clearly seen in the IASI retrievals. So the IASI retrievals are in the A, B, and C tiles here, and you have radio sounding measurements here that also capture the dry descending air. And the profiles, then the retrieve profiles agree well with the radio sound measurements, and it was noted that such profiles are extremely rare, so the forecasters were quite happy to see this, that we could capture this. There was another study with another Shapiro-Kaiser cyclone presented during the EUMETSAT user conf in Tallinn, and that concluded positively on the potential of such products to support forecasting in the context of these non-convective storms as well. Okay, I'm going to tell you now about a case we looked at qualitatively 2 years ago, a massive storm that hit southwest of France with large hailstones that destroyed roofs in entire areas before the rain flooded the indoor and made them totally uninhabitable. The severe animation here to the lower left gives you an impression of the weather situation that day. It so happened at the time that the forecast didn't anticipate, it seems, much instability in this area here. Interestingly, also, the different models gave slightly different impression of the structures and coverage of the instability. There were signs of instability in the IASI level 2 products, though, and that's illustrated here with the lifted index. And that's how we saw this could be an interesting complement to the forecasts. And the reason why this stability, IASI saw instability, was because we retrieved warmer profiles in the lower layers than the forecasts were telling at the time. And later that day, this is where the storm raged. Okay, a quick illustration of a long study work performed in partnership with the Hungarian Met services that shows the stable and unstable structures seen from IASI products, well separated by the cold front passing by. And the weather situation is illustrated here with the geo imagery to the right. At this stage, we should really try and extrapolate from there what IRS will bring in terms of spatial coverage with the contiguous pixels and the temporal sampling. To continue, I'd like to come back, and I'm nearly finished with that, on one notion I introduced before, is that hyperspectral have a lower sensitivity near surface. And one direction that is understood correctly currently is to try and support even better forecasting, would be to blend the satellite products with surface observations to derive a stability information that is more reliable and that remains totally independent of the forecast that the forecasters could use in complementarity to the NWP outputs. So we know that the surface state is a key ingredient in the convection, and accurate knowledge is hence necessary to derive most reliable stability information. So blending the satellite data with ground information, we can get a more accurate and increased CAPE information as I'm illustrating here. And I think that corresponds to this pixel there. We've done the same thing with the forecast, actually, which we blended with, so the profiles which we blended with the surface observation. And we saw that we also were able to increase the CAPE. In that case, in this study case, the IASI lapse rate was higher than in the forecast, and so yielding a larger CAPE. But there were other cases where also IASI showed limitations, so we need to study that further, obviously. Okay, I'm now going to the end of my talk. There's one last application which I want to highlight and stress really importantly, is the possibility to derive 3D informations. And this slide summarizes work that is ongoing to derive 3D wind products from IASI, taking advantage of successes overpass here of METOP B and METOP A, but now METOP A, B, and C actually. And in the overpass region, to infer atmospheric motion vectors from the temperature, humidity, and ozone patterns and how they change from one pass to the other pass. And that's achieved by our colleagues Olivier Hautecoeur and Régis Borde, and contribution of external lab from INRIA in France, using the 3D optical flow. And there's no circulation model embedded, that's also forecast free. And we know that the wind information is key in weather forecasting, whether in numerical weather predictions or for direct use. So there is big ambition with IRS to derive also 3D winds information. Okay, and with that, I'm coming to the end of my talk. So just to wrap up and summarize what we have said and give an outlook on the future hyperspectral level 2 products. There is a large palette of meteorological products: temperature, humidity, ozone profile, surface temperature, clouds, and many more. There is also a long proven heritage from EPS IASI. There is also at hand the IRS IASI level 2 service, whereby products are available within less than half an hour from sensing, and that's in time for nowcasting applications. So that's available for you also, users, to make experience and prepare in view of MTG IRS and IASI-NG, obviously. IASI-NG will yield improved sounding performances and species detection capability. MTG IRS, the big strength will be the unprecedented 4D look onto the atmosphere that it will allow, and that will be key to monitor the atmospheric dynamics. So looking ahead, the IASI services are available. That's an opportunity to prepare for the future missions, use them, give us feedback to evolve the services and the product. There is a great potential for nowcasting, atmospheric composition, air quality, marine, NWP, regional, global applications via the 3D winds. We are studying also the level 2 assimilation. I haven't touched on that, but if there is interest, we can discuss it. And to build up, extend the climate records initiated with EPS. And of course, there is a synergy LEO-GEO to be exploited, and also instruments. So for instance, using the Sentinel-4 and 5 together with the imagers and the hyperspectral sonders, but that's to be further studied and exploited. And with this, I'm done. I appreciate very much your patience in extending this presentation by a couple of minutes more. Thank you, and I'm ready for questions if you have. Thank you very much.
Thanks, Thomas. I think that was quite an interesting presentation, the wealth of information that is coming from the next generation, especially IRS this unprecedented data coming from that. I think we have a couple of questions there. Maybe Rosa, you can show the questions, but we will also encourage you to post more questions. We can take some of them after this session. So I'm picking one of the first questions. That's the dust index question. Is the goal only, this is from Sophie van den Busche, about the dust index, is the goal only to remove those scenes from analysis as for cloudy scenes? About the dust index, Thomas.
Yes, thank you. That gives me the possibility to elaborate a little more. The first motivation for seeking a dust index was when we realized many years ago, when validating the sea surface temperature, that the presence of dust in a IASI pixel was influencing the accuracy of the SST. And so we wanted to have some way of informing about the quality of the SST, which is extremely sensitive. For SST, as we have seen, we need precision of the order of 0.3 to 0.4 Kelvin. So even a degradation of 0.2 Kelvin is significant there. So that was the initial motivation for the dust index, and we're using that information to perform the quality control and flag the quality of the SST. At this stage, within the scope of IASI level 2 or IASI-NG or even MTG IRS, it is not intended to make it an aerosol product as such. This is in the scope of the polar multi-mission aerosol products, the PMAP, for instance, to do that. And by the way, they're using this dust index as a starting point, as a mask, as a starting point to further characterize the aerosols. I hope that answers the question.
I hope so too. I mean, the next one, maybe I pick Dan Lindsay's question on users may be interested in knowing the accuracy of the retrieved thermodynamic parameters versus model values. Have you compared the accuracies?
There's one way to compare the accuracy, for instance, to do that against sound measurements. So that's a direct comparison to an objective independent information. Yes, we have done that. In fact, our American colleagues, especially University of Wisconsin, have done that more extensively than us, and there are a number of papers on that show that the satellite sounding on their own may be limited, and that illustrates the benefits of using the ground measurements, the ground observations in addition. Now we always also stumble against the issue with when comparing to radio sounds, that the collocation uncertainties may be large. There aren't many sound measurements that are exactly collocated in time or coincident in time with the overpass. And in our routine monitoring, we tolerate up to 3 hours, and we know that within 3 hours, a hell of a lot can happen, especially in the lower atmosphere, that will influence the CAPE anyway computed from the sound that we would compare to the retrievals or even the forecast. So another way of looking at the accuracy, but we look at it more qualitatively in terms of significance, and that's part of the work initiated with the ESSL, is to see how well a CAPE signal from the forecasts or from the retrievals relate to the development, to the actual development of a severe storm later. And that is longer, that is less quantitative in terms of accuracy. It's more of a qualitative significance, and it's longer to take. And we are in this process at this stage.
Okay, thanks, Thomas. I hope that answers you, Dan. There is I think I'm picking the question on the lowest height of temperature relative humidity profile, 0.8, is it 0.8 kilometer from the surface is the question.
So, yeah, I can see the question. Okay, just to make sure there is no confusion here, the 0.8 kilometer was the required precision at which the precision in the retrieval of 0.7 or 0.8, can't remember, for IASI-NG was required. Anyway, the retrievals are presented in a vertical grid. in a fixed grid for some of them. And so the altitude will vary depending on the actual surface elevation, because the fixed pressure grid will not vary. But we also plan to provide the surface air temperature and the surface air humidity to the extent that these hyperspectral sonders can get that information. So the lowest height will be the surface air information, but with limitation intrinsic to the measurements. And then the actual altitude will depend where the surface is located with respect to the fixed first pressure point.
I think I should pick one more question related to this comparing temperature and humidity profiles of satellites and radiosones. It's actually asking, do you degrade the vertical resolution of the radiosonde? And if so, what's the best way to do so?
I like the question. Might take a longer answer of me. So yes, there are different strategies to compare the retrievals to the radiosones. The first approach is to compare the profiles as they are presented on the original pressure grid on which they are provided to the users. So that's kind of a level-to-level comparison. Then to evaluate whether we meet the user requirements, we can integrate, and we have done it, we can integrate the satellite and the radiosonde profiles on 1 or 2 kilometer layers, for instance, in the case of IASI, to verify that the accuracy for temperature at 1 kilometer and for humidity at 2 kilometers is indeed in line with the user requirements. Now there are other ways, notably to consider, to take into account the actual vertical resolution of the retrieval at a given point, is to apply the so-called averaging kernels, which tell you the vertical resolution, vertical sensitivity. So you would convolve the radiosonde measurements with the averaging kernels, and so for the areas you know you have no sensitivity to, then you would not make any comparison. So that's a fair comparison of the satellite products. However, when you do that, let's take an extreme example of the lower troposphere, where let's assume we have no sensitivity at all. If you apply the averaging kernels to the sonde, you will have 0. If you apply it to the retrieval, you have 0, and you will make 0 minus 0, and you will have 0. And you will think, oh, I have the highest precision I can think of. But it has to be related also to the fact that the averaging kernel is telling you have no sensitivity. So this is interesting to do, but to be handled with care. I think the 3 approaches are valid depending on the context and whom we are talking to.
Okay. So this is how you did it, actually.
Yes, in the various validation reports, which are publicly available online, from the successive IASI level 2 revisions, the 6, X1, 6.2, etc., METOP B and METOP C, you will find examples, instances of each of these 3 methods. Not necessarily each time, but you will have a combination of 3, yes.
Mm-hmm. There are several more questions concerning the soundings, actually.
Yes,
but I think, yeah, I think it's good. We can eat a bit more into, maybe take 1 or 2 questions. But before that, how does cloud masking work for IRS EPS-SG?
Yes, okay. Yes, I went very fast on on that. So the cloud detection for IRS and IASI-NG is based on the approach that is currently operational with IASI, actually. And so it's a variational method which takes as input the temperature and humidity profiles and ozone, etc., retrieved from the statistical whole sky, okay? And then varies a cloud altitude and a cloud fraction, and with a gray cloud modeling, compute the cost of these different combinations. The cost being the difference between the observation, so the IASI radiances, to simulation including clouds at different elevation with different cloud fractions. And where the cost is minimal, then we think that corresponds to the truth, and that's how we decide whether there is a cloud, if the cost is smaller than the cloud-free cost, and where the cloud is located, and what is the fractional coverage. So the mask is derived from the actual cloud retrieval.
Okay. I think, Thomas, what we will do is we will go to you are the next presenter as well. We will go to the next presentation. We will keep these questions, but, you know, we can take it maybe then, yeah? So that we don't,
yes, sounds good to me.
Don't run over time. So shall we do that? Shall we go to our next presentation, then collect these questions?
Sounds good to me, yes, absolutely.
Mm-hmm. Okay.
So I'm opening the presentation. It's 500 meg, so it's, oh no, it's open quite rapidly. Okay, very good.
Yeah, okay, let's skip. So Thomas will be now presenting on how we can realize this concept of 4D weather, yeah?
Yes. Can you see my screen? Oh no, I need to grab the floor perhaps.
No, we can't see your screen yet.
Okay.
It's a big file, possibly.
Yeah, it is a big file. Oh, hang on. Okay. I apologize. I need 30 seconds to get that.
It's fine, Thomas.
It's loading up. I should have opened it before. I apologize for that.
No problem. You're waiting.
So, meanwhile, we can have a drink.
Yes. I think it's a short drink break for everyone.
Yeah.
Is it opening or sharing the issue? If it is sharing, then...
No, now it's the opening. I thought it was open, but I didn't realize there was a progress bar on the way.
Mm-hmm.
So we are now approaching 80%.
Okay.
Yes, 80, 85. 90, 95.
Keep going.
We're preparing for the launch.
Yes. Not at 100.
No, I'm good now. Okay.
Okay.
So I need to grab the floor. So back to the Zoom. No, where is my Zoom? Yeah, okay. So I'm going to share the screen one again.
Yeah. Yes.
Okay. Okay.
Yes.
Okay.
Audience mode. You can start here.
Okay, brilliant. Okay. So the goal here, that's a project which I'm presenting, but there are many people involved, in fact, in that project. The objective is to generate a realistic communication material, which will be an animated 4D weather cube. So with a 3D view of, you're not seeing my pointer. Up, now you're seeing it, of the different components that MTG, so Meteosat third generation, will allow, and we will go through each of these layers in the next slides. So to provide an animated in space to give the 3D feeling of all the information, but also in time, hence the 4D. And that animation should be a realistic communication material to use, but also we ambition that it is a realistic precursor to further data sets for user preparation. And in that cube, we will have atmospheric composition, as we have just seen, coming from MTG IRS, winds coming from IRS and from the imager, the so-called FCI, convection, the imagery, but also the infrared sounding, and the lightning, so that will betray the storm activity from the lightning imager, which is the other instruments on board the platform, the imager platforms. So for that animation, we selected one meteorological case, which dates back to June 20th, 2013, and where severe convecting storms hit Germany and Central Europe more in general, and that led to a number of floods, and quite pretty severe floods, as illustrated here. So the proxy data are the following. The domain that is covered is Germany. The temperature and humidity fields come from a very high resolution model, sub-kilometric model. I think it's 300 or 400 meter resolution of DWD, run in the ICON HD CP2 experiments over Germany. The wind fields that we're going to use come from MSG Severi, so they are real wind animations of that day. The atmospheric imagery comes from Severi as well in the rapid scan service, and that has been resampled to the FCI viewing geometry and sampling. And the lightning imagery is simulated from GDL. And these are GDL 360. These are real data provided by Vaisala. So now we're going step by step through each of these layers, so you get a feeling of the animation and the notion we want to convey. And what you will see is an exploded view of the ultimate animation, which will gather them all together. So let's try, does it start? That should turn around. Why isn't it starting? Okay. Voilà. So this is the relative humidity, and I will keep clicking. This is very short at this stage. This is only 2 hours that have been compiled to make this preliminary animation. And the idea, as you see, is to rotate in the 3D to convey the 3D feeling, but also to play the animation over time. And that's, you can feel the beginning of that with the animation. And as we will see later that day, or we can see it now, actually, there was quite a number of convective events, so we expect to see the humidity field to rise at the center of the domain. So the atmospheric motion vectors ultimately will come from FCI, but also from IRS. Here is an animation of that day from Severi. So these are 2D wind vectors because they come from the imagery. The clouds are in black here. And then you recognize the wind barbs here. So as the convection starts, then we also have wind vectors all over the place. So this looks a bit sparse. There are actually more wind vectors that can be retrieved, but in this animation, we retained only the good quality vectors. Then comes the imagery from the FCI that shows the convective activity, and you see all the convective sails being ignited and popping up as the day goes. And the last but not least layer is the lightning storm. So what we have here is the Severi rapid scan service of 5 minutes underlying, so in grayscale, and you recognize the cloud formations we had at the beginning of that day. And later, the animation is slower, so we will leave time, and we will see all the convection starting in this area. So the flashes that you see gives an impression of what LI will provide as an information in terms of location, detection, and the flash power and duration is encoded in the disk size and color. The frame rate here is 30 seconds. So that is made to give you a fair feeling of the lightning imaging capability when this is flying in space. And so here it comes, the first convective cells here, and more will come and pop up here. And you will see the lightning events associated with that. So I leave it another couple of seconds because it's nice, I find. The lines here is very interesting. Okay.
Thomas, I mean, just for the information of audience who are not familiar, I mean, MTG imaging service will have a lightning imager and the flexible combined imager. So flexible combined imager is the successor of Severi, and the lightning imager is the new mission.
Absolutely. Thanks so much for completing that. Yeah, I can show the slide again. I forgot that one. Or did I? No, I forgot it. Yeah, I can show the slide again that present the three instruments. Okay. Well, that was it basically. So such an MTG collocated data set will be a novelty to the MET community. So again, beyond the nice animation for communication purposes, we want to ultimately to grow such data sets to evolve into test data sets. And significant efforts will be needed to fully exploit these data sets. And comments are welcome now and later as we work with them on how to address the challenges of the visualization and analysis of MTG data as a block. And with it, I think that's that's it. Thank you.
Thanks, Thomas. I think a lot of computational effort as well there, right? I mean, to generate all these data from models and observation.
Yes, absolutely, yes. And this involved many different teams. I gave the names of the lead people in the beginning, but within EUMETSAT, within the German Weather Services, and an external contractor, design data that do actually make this animation.
Okay, thank you. Rosa, can you present the questions, please? I think we have a couple coming. I think we can take the one that is directly, the third one that I see on the screen, what software that's directly related to this presentation, right? What software do you use for visualization, satellite image animation, 3D simulations, etc.? Is it operational software?
So for that animation, for the purpose of that animation, the software is one software used by the external contractor, and I don't know what it is. We internally at EUMETSAT, each different team uses IDL, MATLAB, Python, Julia. Now is a brand new language. It's very powerful, but there is no such visualization software that I know of to make such 3D or 4D animations, but maybe Sarika and Stefan can complete, because that would be an interesting feedback perhaps to take.
Stefan, do you want to add something there?
Hi, this is Stefan Brzezinski. Just to say that we are working with the open source and also commercial manufacturers to develop such software. And that is the purpose of having this presentation today, that we stimulate the development and the discussion around how to best visualize such data for both operational purposes, for research purposes, but also for communication purposes.
I think there's an interesting question. The 4D cube, will that be made available to the user, and if the user can update or change it as needed?
The 4D cube as an animation, I believe, yes, will be made available. The underlying data, I don't know, we haven't discussed that in what form that could be presented, because it will need to be packaged a little bit. I'm not sure of the model data from DWD. Maybe that's something we will need to check with them as well.
Okay.
On that question, if I may, we are really grateful for any feedback from the community here joining this event today about any specific needs you may have regarding such a 4D cube, which time and spatial area it should cover. And if we have a good set of user needs identified, we will, as Thomas already indicated, we'll do our best to generate such a data set, which would then be made available.
There's a comment that it would be great to have this in Python. I think it's a comment.
Okay, an action for the PyTroll, perhaps.
Yes. I think we are running into Pierre's session now. So maybe we take the Thomas, you will stay till the end of the session, right?
I will definitely. Before you go on, if you want, I can share this one slide where you can explain again the three instruments, IRS, FCI, LI, in the context of the MTGI and MTGS.
Okay.
Yeah. Can you see it?
Yes.
So that's what you were introducing before, yeah.
Yeah. Yes. Stefan, do you want to say something?
No, I think it's been said.
Okay.
Okay.
So then we move to the next presenter. Thank you, Thomas.
Thank you too.
We had 2 presentations. Well done. Thank you. So we move to Pierre Coyer for our next presentation. Pierre, I won't risk pronouncing your institute's name in French. I think it is Free University of Brussels. So please take the opportunity to introduce your institute in French and start your presentation. Thank you.
Okay, so thank you. Indeed, I'm coming from the Université Libre de Bruxelles. And it's a bit of a challenge to come after Thomas and all these nice animations. So I will not talk about thermodynamic product. I will move now to the atmospheric chemistry products. And so a brief outline of the talk. I will first talk about IASI and atmospheric composition measurements from IASI, the heritage that we have. The first thing I want to show is what information is available in these hyperspectral infrared measurements. What do they carry really? And then I will move to some applications, first in terms of global mapping with the example of carbon monoxide. And then I would like to go further by going deeper into the spatial aspect by tracking down emission point sources. The example here will be ammonia. The third application will be that of the monitoring of extreme events or unpredictable events like volcanic plumes and fires. And finally, but not the least important, is what we are doing in monitor the long-term changing atmosphere and thereby the monitoring of protocols. Second part of the talk will be on the new, let's say the next generation hyperspectral sounders, so IASI-NG and IRS. They are really different in what they will do. I will try to show that. And the last couple of slides will be just on showing what operational atmospheric composition products we have, so their availability and the future plan. But let me start then with the heritage from IASI. So I'm not detailing IASI. We have heard already quite a bit in the previous talks yesterday and also in Thomas' presentation. We have 3 IASI currently in orbit, and I think the key point for atmospheric composition lies in the fact that the IASI provide near global coverage twice daily, as you know, with overpass time in the morning and in the evening. Just as a reminder, in terms of atmospheric composition, a lot has been done in the past years with UV visible instruments. Here we are with hyperspectral infrared instruments. Of course, we can also measure during the night. So global coverage is achieved with IASI with a medium spatial resolution for atmospheric composition, a 12 kilometer on ground pixel size. The instrument itself is very good, so high spectral resolution and very good radiometric performances. And what is important is that we are looking towards 18 years of global measurements with IASI, and these are to be followed then with the measurements of IASI-NG. And this is done with exceptional stability. So as you know, the priority one of IASI was to contribute to weather forecasts, and this is an important instrument in that respect. But I will not talk about that. What I want to focus on is the fact that IASI is capable of measuring up to 30 trace gases in the atmosphere. This is much more than what was anticipated before. And that goes with a series of applications, of various applications in terms of atmospheric composition that I will try to highlight in the talk. So first point, what information do hyperspectral infrared measurement carry? The slide here shows you an example of a IASI spectrum, level 1C, and highlighted there are the main spectral signatures to be found in the spectrum. These are due mainly to the greenhouse gases. We see spectral signatures of carbon dioxide, methane, nitrous oxide, water vapor, of course, and then also quite some strong signatures from ozone and carbon monoxide, which are more reactive trace species. It's important to recognize that we are dealing with an integrated view of the atmosphere. So we have mainly information on the total column, but on top of that, we can retrieve different pieces of information on the vertical. This is true for not all the species, but certainly true for ozone, where we can distinguish between 3 and 4 independent pieces of information and can certainly separate tropospheric and stratospheric column. For the tropospheric species, we have a bit less information. We have main sensitivity in the middle troposphere that is to be seen for carbon monoxide, sometimes a little bit more than just one total column. But for the greenhouse gases, mainly sensitivity in the middle troposphere. So keep in mind that we are measuring a column with some profiling capabilities. So I don't want to go into the full list of the 30 species that have been detected, but this is much more, 4 times more than anticipated. And all the blue ones are those for which we can now acquire global distributions daily. So it goes beyond the strong absorbers, also for some of the weaker absorbers, we can provide global distributions daily. I will show the example of ammonia, but we also have that for a series of volatile organic compounds. Other species we only see in concentrated plumes following volcanic eruptions or large fires. Some are really exceptional. The 2 that are highlighted here in red, ozone and nitric acid, for these 2 species, we have good sensitivity in the stratosphere, and that opens application also for stratospheric chemistry monitoring, of course. So I will not show more on the aerosol than that slide, but on top of the trace gases, I think it's really important to realize that with the hyperspectral infrared sounders, we are now in a position to provide good information on aerosol. This is mainly a coarse mode aerosol, but the main aspect is because we are covering a large range of the infrared without any gaps, we can see the different spectral signatures. We can differentiate the aerosols as a function of their source. More particularly, what we can certainly discriminate are wind-blown dust from volcanic ash or sulfate aerosols, or even from ice crystals. And even different volcanic eruptions will show up with different ash signatures, and these can be identified in the IASI spectra. I think for the future, this is an important aspect as well. But so the applications that I have chosen are mainly on the trace gases. The first one, I want to illustrate what we can extract in terms of information when we make global mapping of atmospheric composition. So the example is that of carbon monoxide. What you see here is an animation month by month of carbon monoxide in the year 2015. And you can see, so blue are low abundances, and when we move to yellow-red, these are larger total columns of carbon monoxide. So clearly in such animation, what this reveals are the areas, the regions where we have large emissions, for example, in East Asia or in the Southern Hemisphere, these are due to fires. So the first application is probably on the better understanding and better quantification of the emissions, being either anthropogenic or due to biomass burning. But with traces like carbon monoxide, which are reactive in the atmosphere, we can go further, and in improving the atmospheric budgets of other species. I have taken here one example publication by Jean-François Muller, which has in fact used the CO distribution from IASI to put new constraint on the levels of OH in the atmosphere, OH being the principal oxidant in our atmosphere. So I should have mentioned in terms of emission, what we are seeing here is the year 2015 with these huge fires that have occurred in Indonesia. And here again, quantifying these emissions is an important aspect. So going further into the mapping, I'm showing now the example of ammonia. It's different from carbon monoxide because ammonia is a short-lived trace gas. Its residence time in the atmosphere is not more than a few hours. So basically, we expect to see strong concentration gradients in the spatial distributions. The concentrations will be larger, of course, close from the emission sources. So the area chosen here is the Nile River and the Nile Delta. And the first thing I want to say is that when we are talking about global distributions daily from IASI, this is a bit of a selling because IASI is not a mapping mission. We have gap in between the measurements. And these are well seen here. This shows just a single overpass of IASI. Each circle represents a pixel of IASI, and the colors blue to a red shows you increasing abundances of ammonia. So with a single overpass, we can see already where the concentrations are largest, close to the Nile Delta and all along the river. But we don't map fully the region. In fact, this mapping can be done only by averaging or accumulating data over several days. I want to show you this. So this is what we get after 2 days, a second overpass of IASI, and then a third overpass, where is the pixel size that are varying because we are looking now off nadir as well. And this is what we get after a week. So after a week, the map is almost full. After a month, it is completely full. And there we can see the details of the concentrations all over the regions. It's still pretty noisy, even after 1 month. This is what we get after 1 year. It's getting better. We start to see fine details. And after 10 years of averaging, we have this beautiful view of the ammonia pollution in that region. So everywhere where the concentration are largest, this is where the emissions are also larger. Of course, we have done that by sacrificing everything on the temporal sampling. So everything is lost regarding the variability, the temporal variability of ammonia, but we have gained a big insight onto the emission sources. In fact, in these 10 years average distributions, we found very localized point sources to be seen here, which are due to industry. These point sources, which are, let's say, smaller than 50 kilometers across, we've identified more than 500 of them around the globe, and we have been able to attribute these to either very large agricultural complexes or to several types of industries, and a few examples are shown here. And for each of these point sources, this is an important point, we have quantified the total emissions of ammonia in a simple manner for the time being. But the key result is that we found out that many, in fact, most of these point sources were missing from current emission inventory. So with these very, let's say, precise mapping, we are bringing something to the community, which is a better knowledge of the emissions of the various pollutions. Okay, the third application I wanted to introduce is that of the monitoring of, let's say, extreme events. And first, volcanic eruptions. We measure volcanic plumes pretty well with IASI, thanks to the signal of sulfur dioxide, SO2, in the spectra, and also ash. And I think it's fair to say that IASI hasn't missed a big eruption since launch. We've captured all these large SO2 plume, and we can follow the volcanic plume along that transport. For SO2, we can estimate the total emitted mass, and this has climate implication because SO2 quickly forms sulfates in the atmosphere, and this, as you know, have a cooling effect. So it's important to have this information. But beyond that, working on detecting the volcanic plumes is important for another type of application, much more concrete maybe, which is to alert quickly when an eruption has taken place. And the main uses of such a system, which has been implemented and it is hosted at the Belgian Institute for Space Aeronomy. So the main users are the Volcanic Ash Advisory Center. So basically the system integrates the EASI, but also a series of other sounders which have different overpass time. And the aim is to quickly alert the Volcanic Ash Advisory Centers when an eruption has taken place, and also to tell more precisely where the plume is located, and the VACs themselves transfer this information to the airline companies in order to avoid airplanes to fly in the plume. So it's a very concrete application, but I think it's an important one. So in terms of extreme events, we are also doing good with the hyperspectral sounders in measuring fire plumes with different types of tracers. The animation shown here is using carbon monoxide, and you probably know that the past 2 years have been extremely severe in terms of biomass burning. There have been huge fires in Siberia, also in Amazonia, Australia at the beginning of 2020. And the animation shown here is are the fires from California. So you see it's only this excess of CO that is plotted in this animation. So everything which shows a deep red is where the sources are located, and you will see then the fires coming from California being transported by westerly winds towards Europe. Then the last application I wanted to mention is how the hyperspectral infrared instrument contribute to the long-term assessment of our changing atmosphere. We do follow atmospheric composition, of course, now since more than 10 years with EASI, and for a series of parameters, for a series of trace gases. I'm showing you just one application, which is that of stratospheric ozone. So the figure shows you 12 years of stratospheric ozone. This is the view of the South Pole during the period of the ozone hole. So we have 12 years of ozone hole monitoring with EASI. 2015 was a record high ozone hole in the EASI period, so over this 12 years period, whereas 2019 stands out as a very small ozone hole year. In 2020, this year, these are very recent measurements, we are again in a pretty severe ozone hole situation. So of course, it's nice to see. It's important with respect to assessing if the Montreal Protocol is bringing the expected result. But we have to quantify this better. There are different ways to do that. This map this plot on the right-hand side shows you a simple way to look at the ozone hole. It's just the ozone hole size fraction for the 12 years. But we want to do more and try to see if there are trends in this signal. And getting trends from 10 years of atmospheric measurements is usually very tough. But we can do that with EASI thanks to the numerous measurements that are available. And the plot shows here at the bottom left is taken from a recent publication of Catherine Wespès. It's for stratospheric ozone, and what is shown is the trends over a bit less than 10 years. We see an increasing trend in the southern hemisphere. This is good, shows a recovery of the ozone layer, but at the same time, a decreasing trend in the northern hemisphere. So it's in fact extremely interesting and important to look at these variations on the long run. So it's a view on how our anthropogenic activities are and that the atmospheric dynamic is modifying the atmospheric composition. But we talking about trends, it's certainly also key to look at the greenhouse gases. So this is a slide taken from Cyril Crevoisier group at the LMD, showing the time evolution of CO2 on the left-hand side and methane on the right-hand side, and for both hemispheres. So we are getting, thanks to the 3 different EASI instruments, a very nice and homogeneous time series. We see the seasonal variation But on top of that, a clear trend again for the greenhouse gases, a 20 ppm increase in CO2 and a 100 ppb increase in methane. For the two greenhouse gases, this is about a 5% rise over the 12 years. So a clear view there on our changing climate with EASI. So what is coming next? What will the other next generation hyperspectral infrared instruments be? EASI-NG and IRS. So EASI-NG will be very similar to EASI, as you have heard in the previous talk, also yesterday in the hostess talk. So it will continue the record of EASI. The spectral domain is exactly the same. The sampling is also similar with the 12 kilometer on ground pixel size at nadir. But the fact is that EASI-NG will have twice better instrumental performances and will provide more precise measurement, and I will try to highlight that. IRS will be completely different in its philosophy. Thomas illustrated this very nicely in his talk. It will not be as good in terms of spectral resolution. The spectral coverage will also be non-contiguous, but we will benefit from the spatial resolution that is will be better than with EASI-NG, but especially from the sampling that will bring a new view of in the changing chemistry. So let me start first with a few achievements expected from EASI-NG. The mission objective are definitely to assure the continuity of EASI for all applications, including atmospheric chemistry. Then another objective is to improve the performances in the different parts of the atmosphere, but especially close to the surface, in the boundary layer, and in the transition region between the troposphere and the stratosphere. And finally, to improve the precision of the retrieval for all species. So will we achieve that? Well, this is a bit more of a technical slide. Dorothea showed something similar yesterday with carbon monoxide. What this shows, in fact, is how the measurements respond to a given perturbation in the concentration of trace gases. So we are focusing here on carbon monoxide, so only on the black curves. And on the top panel, we have the response of EASI to a 10 ppbV perturbation of carbon monoxide, and on the bottom, EASI-NG. The red dotted line on top shows the EASI noise, it's above 0.2 K, and in the bottom panel, the blue dotted curve is the noise of EASI-NG. So basically, what you see in between these noise curves and the top of the rotational lines of carbon monoxide is the signal that we can extract with for a given perturbation. And it's clearly much larger, a factor 4 again with EASI-NG than with EASI. Shows you how much more sensitive the instrument will be to atmospheric composition change. So this translates directly into the level 2 products. We can see that very clearly in this plot. These are simulations. So we are looking at how well EASI in red or EASI-NG can reproduce a truth profile, here a reference aircraft profile that is shown with the black line. There are two situations. On the left-hand side, we are in winter. On the right-hand side, this is the summer. I don't want to go too much into describing this, but if you look at the differences between EASI-NG and EASI, it seems obvious that EASI-NG will perform better throughout the profile, but especially low down, close to the surface in the boundary layer. So that will be extremely important to better improve air quality applications. What about IRS? I am trying here to summarize everything that I said in a single figure, all the application areas that will be accessible with the hyperspectral infrared sounders. So will IRS contribute to all of them? It will probably, but not so much when we are talking about global tropospheric chemistry or global stratospheric chemistry. The main contribution of IRS is certainly where for processes that vary rapidly in time and space. For example, air quality, we will be able to measure the diurnal cycle of air pollution, the monitoring of unpredictable events, volcanoes, fires, industrial accidents if they happen, monitoring of point sources, and of transport, certainly. So to illustrate that, I want to show a couple of simulations for IRS and IASI-NG, and these are for ammonia. So again, ammonia is a short-lived species that resides mostly in the boundary layer. So with this simulation, I also want to bring an aspect on which I didn't really touch upon, but Thomas mentioned that in his presentation, is the varying sensitivity that we have towards the surface atmosphere as a function of the thermal state of the atmosphere. And let's say it in another way, as a function of the thermal contrast being defined as the difference of the temperature of the surface and that of the boundary layer. So these simulation experiments are made every half hour. You can see on the left-hand side thermal contrast. It's above the Netherlands. We are in this first slide at 5:30 in the morning. Thermal contrast is low everywhere above the ocean, but also above land. The second plot is what we would like to reproduce. This is a model distribution of ammonia at very high spatial resolution. So the question is, what will we get from these spatial variation of ammonia with IRS and IASI-NG? So I'm starting this first result is at 5:30 in the morning. So first answer that is obvious. With IASI-NG, we will not make any measurement at that time of the day, so nothing to be seen. IRS will measure every half hour. But will it measure everything from the boundary layer composition? Not really, because of thermal contrast. So this first distribution at 5:30 in the morning is very noisy. You can think that maybe we see a little bit of increase of ammonia above land, but still very noisy. But what happens when we move at 9:30 in the morning? There, thermal contrast has increased significantly, more than 10 degrees over land. It's still, of course, very small above ocean. Again, the second panel shows you the reference model distribution of ammonia. And again, the question is, what will IRS show and what will IASI-NG show? Let's start with IASI-NG. IASI-NG, under these conditions, 9:30, will make extremely accurate measurements of the atmospheric composition. The distribution that you see is very smooth, almost no noise at all, and you can recognize the main patterns of ammonia that we want to see. However, because this is not a mapping mission, again, there will be gaps between the pixels, and also because the pixel size are larger, the distribution will be very much smoothed out. IRS, on its side, will provide a very nice view of the spatial variability of ammonia because of the smaller pixel size and because there is no gap in between each of the pixels. It will be really an important mapping mission for atmospheric composition. And IRS will operate every half hour. So this animation shows you basically everything that we will measure with IRS and then with IASI-NG twice a day. So not so much in the evening, but when the thermal contrast had to increase, then the distributions will be very nicely reproduced, as you can see, throughout the day. So we will have a first view on the diurnal cycle of pollution above Europe. That will be the clear gain of IRS. A couple of slides now on the products that are available. And I should mention that when we talk about operational products, these have been developed mainly in the framework of the atmospheric composition SAF. For IASI and IASI-NG, two products are already operational. Carbon monoxide and SO2 are operational, so they are distributed to users through the EUMETSAT system. Ozone profiles and HNO3 profiles are in demonstration, so they are produced and distributed, but not for pixels. So this is not yet fully operational, but it will come very soon. And the other couple of products that you see here should be implemented in the next months or next year. We will enter in 2021 into a new phase of the atmospheric composition SAF, and the portfolio of products will there be augmented by considering also the total columns of carbon dioxide and methane and dust altitude. For IRS, the portfolio of products will be smaller, at least at the beginning. We are targeting only a few of them, carbon monoxide, ammonia, for the reasons that I've mentioned before, but also the greenhouse gases, CO2 and methane. I should mention that the number of users is steadily increasing. The products are already feeding large programs like Copernicus through the atmospheric monitoring service, also the climate change service. They're also feeding the climate change initiative of ESA with aerosol, ozone, and greenhouse gases measurement. I mentioned previously this service for aerial safety, the SAC system, and we are contributing with the IASI ozone measurement also in the tropospheric ozone assessment report and a series of other projects. More on the archived products, they are currently archived mostly on the IRS, the French IRS database, not only the operational products, also some that are currently in research mode. So these are available for download, and as you can see in the bottom panel, they are heavily downloaded by researchers worldwide. And that was my last slide, and I'm leaving you with this a nice animation for a series of trace gases, and I thank you for your attention. And I welcome question, of course.
Thanks, Pierre. We wait for a few moments for the people to type in the questions, maybe. It was an interesting presentation. I think it still proves the complementarity, right? I mean, you have, while it is clear that IRS cannot have a global picture, you get much more resolved and mapping facilities over Europe, and with its high temporal resolution, you capture almost all the variabilities that you see. I mean, you mentioned dynamic variabilities as well. Well, EASI only has, IASI-NG will have only 2 overpasses. So great presentation. Let me just check whether we have questions. Just one question from my side. Do you also look at CRIS or the US satellites?
So we don't, I mean, in terms of processing, we are not doing that ourselves, but they are, of course, very complementary. CRIS has an overpass time, as you know, in the mid-afternoon, or in the, and this is providing better sensitivity to some of the trace gases because, again, the thermal contrast is better. I think it is interesting, and this is probably to put in the future prospects, really put the two together to get this first view that we would like to see on the diurnal cycle of pollution. So with CRIS and IASI, we would have 4 measurements a day. It's not yet a lot, but it would be the first time that this would be achieved. I haven't yet seen anything really done in terms of this combination of the 2 sounders, but the possibility is definitely there.
Okay, thank you. Now looking at the questions, I think I get one question here for you about information on the vertical profile for sulfur dioxide and forest fires.
Okay, this is a very good question. So I in one of my slides, but I didn't describe it very much, but we are getting, I would say, extremely good information for volcanic eruptions on the altitude of the volcanic plumes because of the altitudes of sulfur dioxide. The estimation that we had is, let's say, 1 kilometer uncertainty on the retrieval of sulfur dioxide altitude, which is an important information again when we are thinking of the application for aerial safety. So we can give that information to the users as well. For forest fires, good question. This is more in the research mode. We are trying to get this information as well using the vertical profile of carbon monoxide. But there are a couple of traces which are also quite sensitive to altitude. For instance, C2H2 is a good one. So we are currently looking into that. I think this will be an interesting product for the years to come.
Okay, thank you. While I think there's one more question for you from. Can you go ahead? I think this is the one. which new molecules do you anticipate as operational level 2 products from IASI-NG from Anuduria?
So in terms of operational level 2 products, when I talk about operational is what is produced centrally at EUMETSAT and then distributed through the EUMETCAST system. So in the pipeline, so for the moment we are having, as I mentioned, carbon monoxide, SO2. What will follow is SO2 altitude, respond also to the previous question. And then we are looking to ozone being operational, nitric acid very soon. What will follow next is ammonia total columns, dust and ash, optical depth. These will be important. And then in the next phase of the ACSAF, as I mentioned, carbon dioxide, methane should be in, as well as the dust altitude from our colleagues at the Belgian Institute for Space Aeronomy. And greenhouse gases will be provided by the LMD. So this is for the moment what is planned in terms of operational products.
As for operational level 2 products or operational products from IASI-NG and IRS centrally developed products we have, and also the SAF products, we have a table provided in both EPS-SG and MTG web pages from EUMETSAT. Pierre, also you also showed a map of ammonia over the globe.
Yes.
How is it? I mean, so you also showed this that how you missed this temporal sampling from that picture over the Nile. So how do you anticipate with IRS over Europe for ammonia?
So this is the simulation that I showed at the end was ammonia. So I think it will be extremely good. We are very excited to have these IRS measurements because of this half-hourly sampling. So maybe during the night when thermal contrast is low, we will not get such a good sensitivity to boundary layer pollution, so really the air quality application. But throughout the day, I'm pretty sure that in most seasons, we will get a very accurate view, especially for ammonia.
Mm-hmm. Okay, let me just check whether you have some more questions. I think not, but I think the rest of the, okay, there is one more coming up. I think there's a question. Can you go down, Rosa? Okay, let's just come up there. To what extent are the ozone products and the ammonia products really used by authorities for tracking Montreal Protocol or tracking ammonia emission inventories?
Okay, this is a tricky question. Oh, they are used by authorities. There is regularly an update on ozone, which uses a series of information. And IASI is starting to really contribute with the 12 years of measurement that we have. Of course, tracking the size of the ozone hole or how much ozone is varying year to year doesn't bring as itself an information on the Montreal Protocol. But what I have shown in terms of trends is getting there. So 10 years of measurement is not a lot to get the trend of ozone, which is not really really large. But we are starting to see it, and I think this is extremely important. Various groups are looking into their own instruments and are getting the same types of answer. But we are only starting to come into this this time where we can get the trends right and inform the authorities. The same was true for the ammonia emission inventories. I don't think that they are used yet by the authorities, but this is a first view. So it will be the first step into improving the emission inventories, and then maybe taking measures for a sustainable nitrogen management, which is currently not the case. So these are things that we are looking at very, very carefully. So I'm convinced it will be used very soon.
Okay. I think you had an interesting question answer session, Pia. I guess this was good.
I agree.
So will you be happy to, okay, there's one more. Please don't go away. Do you think IASI-NG will be better to see N2O than IASI?
It will be better. N2O is tricky because it's a very long-lived trace gas. There are different groups working now on the retrieval of N2O and trying to see if we can get some of the spatial variability and more than that, if we can detect sources of N2O. But it's a difficult product because you need a very high precision into your measurements to see the very small variations. So IASI-NG will for sure be better. It will have improved sensitivity towards the surface, and it will improve on the entire atmospheric column, as I have shown for the other products. So clearly, yes, it will be better than IASI.
Okay. I think, will you be happy if I give the floor to, because I don't see any more questions for you, will you be happy if I give the floor to Thomas for answering a couple of questions? Thank you, Pia. So Thomas, are you there still?
Yes, I am, yeah.
Okay.
Hi,
I think we can take a couple of questions for you. Will that be okay?
Yes, sure, yeah, absolutely, yeah.
Okay.
My pleasure.
I think there are still, I saw some more questions on, let me just say, let's take that one on the
first one is the data set, isn't it?
Yes, okay, then please do that, about data sets and case study for 2010.
Yep, okay. So indeed, the LI were simulated, unlike the imager, to serve as proxy for FCI. And this was used using GLD 360 data, which is a ground-based network that observes lightnings. That's run by Vaisala. And I've read that they started in 2009. Now, having that said, whether this is possible for 2010, I don't know. But if the author of the question could contact you, Srerika or Rosa or Stefan offline afterwards to tell maybe which day he or she would be interested in, that's something we can pass on to the LI team and see whether we can do something about that, if there is an interesting case there.
Yep. Okay. There's a comment actually that the nowcasting SAF CDOP4 proposal has service management of MTG sound at the IRS level 2 files in order to be compatible with software as Makaidas 5 or similar. So that's a comment we had related to the previous presentation of Thomas. There is also, I think these two questions, yeah, it's also for you, the information content of the soundings in the boundary layer regarding temperature and humidity.
Yes.
5, yeah.
So maybe I'll get back to one slide.
Yeah.
And that would be this one. So let me just grab the flow now. Share screen. Yes, and that would be the screen 1. So now we are back to the cumulative degrees of freedom.
Yes.
And so if we say the boundary layer is the first 200 or 300 hectopascal, of course it varies. Then the question is, what is the information content? And we see that there is not, it's difficult to get the first piece of information for the first 100 hectopascal. We are hardly there. We're not there with IASI. We won't be there with IRS, IASI-NG perhaps. But that is a very generic answer. And such plots as I'm showing have a number of assumptions behind. To answer fully that question, qualitatively is that there won't be much resolution that we can resolve the structures within the boundary layer, like to within 100 or 200 meters. That's not possible. So fine structures of that scale, they are not at reach for such instruments. But certainly a partial column information of humidity and some gradient in the of temperature, some lapse rate could be accessible. Actually, I have another slide just to complete that, but I have to unhide it. Yep, which I had foreseen. So in our routine monitoring, we are monitoring the value of the profiles by comparison against zones. So we are monitoring the temperature profile as such, the humidity profile as such, and you have seen example of that. But we're also looking at the lapse rate. And the lapse rate, we are looking at different scales, so from ground to 500 hectopascal, or from 850 to 500, which would be like just above the boundary layer and the mid-troposphere, and within the boundary layer, so from ground to 1.5 kilometer. And that's a scatter plot of the lapse rate we would get within the boundary layer from IASI as compared to the zones. So we see that there is a good agreement, globally speaking, now for the unstable situation, which is the one that are very interesting for nowcasting, obviously. We would need more specific data set. We don't have enough of those that we can make robust statistics. But there is an indication that there is some useful information in the temperature profile already in the boundary layer. And now this will also vary from scene to scene. If there is a high surface temperature in contrast to the air temperature, so if the skin temperature is high in comparison to the surface air temperature, we have a favorable thermal contrast that Pierre has introduced for detecting low tropospheric species. The same applies to temperature and humidity sounding. So in some situations, we would have more favorable situation to perform a sounding there. Hope that gives elements an answer to that question.
Good.
You want to grab the floor again?
Yes, Rosa has to share. I think we can take maybe one more question and then we try to answer the rest offline, yeah? Okay. Do you want to answer the question on IASI 3D wind, if you have evaluated that, and if you have any reports and documents that?
Okay, so it's not at a stage yet where we can disseminate products. This is now becoming imminent, but this is still in the development and validation phase before it can run routinely. And I don't say operational in the sense that it would be a routine production plus validated, but at least that it can run routinely. It is more for early next year as for now.
Okay.
But if that person wants to talk more specific details, we can forward and put it in touch with the wind team within EUMETSAT.
I think that's a good move. I think if there's more details needed, obviously we can contact the specific expert. Thanks, Thomas. I think with this, we should wind up. We will take all the questions on board and we'll answer them the next couple of days. Like I said, we will make available all the presentations and the recordings, the question and answers, etc., to you, to all the participants, to all the registered participants. Let me just remind you to go back to the polls area in the slido.com, give your comments, and also try to answer the questions that will really help us in the future webinars. Also, I really hope that all the sessions, that all the talks that are presented here today and yesterday would have helped you to prepare for the next generation hyperspectral infrared sounders. I mean, to trigger your developments and scientific advancement. I would hope that has helped you. I also, on behalf of Stefan, extend my thanks to everyone who participated the webinar the last 2 days, today and yesterday. I also thank all the speakers from yesterday and today, all the EUMETSAT and non-EUMETSAT speakers for your contribution. Also, thanks, Rosa, for your excellent technical support. With that, I close the event.